So in this particular case, we have an object moving to the right. It has a net force to the left. So what is to the right normally mean? What direction do we call to the right? Positive. All right, so that's a positive motion, right? And we have a net force to the left. So if it's already moving with a positive motion to the right and you apply a force towards the left, what's going to happen to that thing? It's going to start slowing down. Right. It's going to start slowing down. So if we now look for a velocity time graph which has positive motion but then slowing down, which one of these velocity graphs would be reasonable to look at? All right, there we've got this one here. We've got this one, this one, this one. We want a velocity which is starting, moving to the left, moving to the right, but slowing down. Anyone? Yeah. E, yeah, because direction is given by, according to our ILEs, what? What's the direction given by? Direction is always the same as the sign of the velocity, right? Direction is always the same as the sign of the velocity. Exactly. So that means it's in a positive direction. This one would say it was in a negative direction and actually increasing in speed, right? This one is a positive direction, decreasing in speed. So the answer there is E. All right, now what is acceleration? Acceleration is the rate of change of with time. Right, the rate of change of velocity with time. So if you've got a velocity versus time graph, what is the acceleration represented by? Slope. Right. So we have E, or we have chosen E as our velocity versus time graph. Is the slope changing? No. The slope is a constant. What else can you tell me about this slope? It's a negative slope. Right. So actually it's a negative slope which means it's going in the negative direction, right? There's a force acting in the negative direction, slowing it down, right? And in fact, force and acceleration are directly related to one another, and we'll find that later. So if we want to look at which of these graphs over here on the acceleration side looks like the one that we need, which one's it going to be? Yeah, C, right. It's going to be below the time axis and it's constant. It's C. If I can get there it is. C. All right, so let's have a look at another thing. So the object's moving to the right and it's got no net force. So what do you think is going to happen now? Who can tell me what to the right implies? A positive direction, right. Now it's moving, but there's no force acting on it. So what do you think's happening? Yeah. It's staying the same the whole time. Right. What law, which of Newton's laws is that? Yeah. Stays in motion. Right. An object at rest will remain at rest. In fact, the way it really goes is an object in straight line motion will continue in that straight line motion. An object at rest will continue in that state of rest unless acted upon by a non-zero net force. Right? So for Newton's first law to apply, the sum of all forces must equal zero, but that doesn't say anything about the original state of motion of the object. It could either be moving or not moving, right? So which of these graphs, velocity versus time, best represents that? What do we say? We're moving in a, I think we said we're moving in a positive, right, direction, and we're moving with a constant v, right? So which of those graphs shows that? B does, yeah, because it's in the positive side of the velocity. That gives us the direction of motion, and it has no slope, so it's constant. So B is the correct answer. All right, let's have a look at the next one. So the object is moving to the right, decreasing speed, stops, then moves to the right with increasing speed. All right, so who wants to walk through this one with us? What does moving to the right mean? Positive, right, so it's a positive motion. Stops, what does that mean? Velocity equals zero. To the right, what does that mean the direction is? Positive. Now, in this case, we've got decreasing speed. So that means it's starting off high and going low. And in this case, we've got increasing speed, which means it's starting low and going high. Right. So which one of these graphs best represents that motion? Anyone else got an idea? Mike? A? All right, so A, what is A doing? Tell me what A is doing. Is it still in this area here? What is A doing? So that's going in the opposite direction, right? It did stop, you're absolutely right, but it's going in the negative direction, right? Does everybody see that? Does everybody see that in this case, what's happened is that the object turned around, right? It's very weird to look at that and say that's an object turning around. But if we know that the direction of motion is always given by the sign of the velocity, we can see that that's the case, right? Okay, so that means which one, Tim? H. And could you walk me through that?
Well, because both lines, they're both going in the positive direction because they're not crossing that the time axis.
Right.
And with the first line, it's since the slope is negative, it's decreasing in speed.
Yes.
And the second line, its slope is positive, so it's increasing in speed.
Exactly. Yeah, good description. All right, so this one is that one. Oh, I forgot to do the AT graph for this one. Someone tell me what the AT graph for that one looks like? The previous one? Yeah. D, yeah. Because? That's true, but there's also another way of saying it. There's no change in velocity. The rate of change of velocity is acceleration, so you can always get the acceleration from the slope of the velocity versus time graph. So let me